All right, example 6. I have my logarithmic function x squared plus 2, which actually, just so you know, that this logarithm exists everywhere because you can't, no matter what I plug in, I'm going to get a positive number, and so I can't get a negative and I can't get 0, so that logarithm exists everywhere. But I am only interested in from -2 to 4. So again, it works at negatives because the square gets rid of the negatives. This is the open case because I am only interested in between -2 and 4, not at -2 and 4. So -2 and 4 are not a part of my function in this example. All right, so find critical values, or find a critical value. Read that over that interval. All right, so the derivative, well, the natural log rule is 1 over what's inside times the derivative of what's inside. So the derivative of what's inside is 2x, and then we usually write that. And you can, this is the steps, but you could skip and go straight to the end, which is 2x over x squared plus 2. Nothing simplifies, so don't cancel out the x's or the 2's. Can't. All right, so there's my derivative. Right, this function exists everywhere because the denominator is never 0. And so find where it equals 0. Well, the only place where I get 0 is in the top part, the 2x. Right, and so there's my critical. It is in my domain, and there's only one of them. And so the test typically is the concavity test, which we usually find the second derivative, which you can't. You can find the second derivative. I'm going to show you an alternative method in case the second derivative is hard. All right, in case the second derivative is a hard derivative, which this one's not terribly hard, but it uses the quotient rule. All right, so I'm going to show you there is another way you can test. You can test using the first derivative and a number line. All right, so if I draw my number line, the biggest thing about the number line, though, is before, when we had number lines, we did the entire domain. We don't want the entire domain. I only want this piece. And so when I draw my number line, I start with an open point at -2. I start with a closed point at +4, right? My interval goes from -2 to 4. I mark off my one stopping point, right? This is where it stopped. That's my critical. And then I still test increase and decrease. So, right, my first derivative I'm testing is what I'm testing. And I want to know when it's positive or negative. So I pick some test points. So -1 over here, and maybe +2 over here. All right, so when I go to my derivative, this is my derivative, I'm going to test it at -1. When I plug -1 in, I'm going to get -2 over 3. So I get -2/3. So this comes out negative, which means it's decreasing. When I plug +2 in, it's going to be +4 over 6. And so that's positive, so increase. And so that means I can still see the shape. It means it's this shape, right? It decreased down, stopped at my critical number, and increased up. And so it does have a concave up shape, right? Based on my number line. And so that means at x equals 0, since it's the only turning point, at the only critical, nowhere else will it turn around again and get smaller. It's an absolute minimum of, well, I've got to plug it into my original function. I would take my original function and plug it in, and when you do, it's not real pretty, right? It's the natural log of 2. Natural log of 2. Would be exactly what it is. That's exactly. And then if you wanted to find the approximate, you take the natural log of 2, plug it into your calculator. 6.9314 is what it is approximately. All right, so that would be the absolute minimum. There is no absolute max in this case. All right, and so those are open. And so I did 3 examples of the closed case, 3 examples of the open case, and I tried to hit the different types of functions you can see. So hopefully you understood that, and if you have questions, make sure you ask.